Can you see the screen? Speak up, please. I'm looking at my, my screen. That means I can't see the chat.
Yes, sir. Yes, sir.
All right. Yeah. So whenever you have a question, please speak up because it doesn't come in the screen. In front of this Notability app, on top of it, it stays behind. All right. All right. Okay. So today's all right. Let us start with a simple stuff. Uh, for example, so you know this. Suppose f(x) equal to uh, x to the power n, and you know another derivative, right? X to the power m. So, so what is f of nx? So what we'll do today is successive differentiation in the beginning, and then we'll go to Taylor series. Yeah, what is f of nx? F prime x m m x to the power m minus 1, f double prime x m into m minus 1 x to the power m minus 2. So you carry on this one, f n x, n is n less than m. This is m to m minus 1, m minus n plus 1 x to the power m minus n, right? Example 1. Example 2, fx equal to sin x. What is f nx? What is f1x? Yeah. Well, you need to calculate. So let me calculate this one, and from next one,
So there is a
well,
cycle of four. It goes like sine, cos, minus, sine, and minus cos.
right. So we want to find this one. So f prime x will be cos x, right?
Yes.
F double prime x will be minus sin x, right? F 3x will be minus cos x, right? And then if 4x will be sin x again, right? So we just write it. So write cos x as sine of x plus pi by 2, right? Hmm?
Yes, sir.
This one, sine of x
X
plus
plus pi.
pi. This is sine of x plus 3 pi by 2. And this is again, this is sine of x plus 4 pi by 2, right? So this way, if nx will be sine of x plus n pi by 2, right? Example 3, fx equal to exponential x. And this is very easy, right? All n fn x will be to the power x for all n, right? Example 4, fx equal to log x, where it is defined, this function, on 0 to infinity, right? It doesn't define the negative axis as well as 0, the point 0. So what will be fn x? So f prime x is 1 over x, f double prime x minus 1 over x square, f3 x is minus 1 square 1 over x cube, right? So what will be fn x? Yeah, maybe I should put this one, but one doesn't put actually. That is fine, no need for it. There's no need of bracket here.
So if
So
3x will be 2 by x cube, right?
yes. Right. So 2 by, there will be a 2 here. 2 times this one. Right. So what will be n? So maybe let me do it one more. 4x is 3 times 2 minus 1 to the power 3 by x power 4, right? And that is fine. So what would be f n x?
n minus 1 prime into minus 1 to the power n by x to the power n
N minus 1 factorial, right?
factorial.
Yes. Minus 1 to the power n minus 1, right? Right, you get 2 here for 3, and for 4 you get 3 by x power n, right? Is this correct? So the reason for doing this simple stuff is actually to fit a polynomial, that will approximate these functions near certain neighborhoods of a point. The aim, ultimately aim, is that. All right. So yeah, so exercise. So calculate f n x for fx one fx to be e power mx fx to be cos x fx to be tan x fx um, log of 1 plus x for x greater than minus 1. Right. Now suppose you have a function, for example, it was 4. So example 5, suppose you have fx is e to the power x sin x. Then what will be the what will be f n x? Hmm?
It should be kind of a recursive series,
It would be
kind of a recursive solution here. Because if we calculate f dash x, then
hmm,
that is basically we know that if there's a product of two functions, it's f dash g plus g dash f. But
right,
here one of them stays constant under differentiation.
right. So e
So
to
we
the power
just
x,
increasing
then
some,
you get cos x
yes, plus fx.
plus sorry, plus e to the power x sin x, right?
That is fx.
That is fx. True. In this case, you get a nice thing, right? Yeah. So this one is e to the power x cos x plus you get fx here, right? So if the whole prime x is e to the power x minus sin x, right? Plus e to the power x cos x plus f prime x, right?
That is 2f prime x. I think.
Why do you get 2x? So this should be, no, why do you get 2x prime x?
No, it's just 2 f prime x minus fx that becomes like that. D to the power x cos x is f prime x minus fx.
Right. That is true. That is true. That is true. Then you can try to find. So one can do this one as e to the power. So here this is minus fx, right? And this should be e to the power x cos x, which is f prime x minus fx plus f prime x. So 2 times f prime x minus fx, right? Is it correct?
Yes, sir.
Anyway, so we want actually in terms of not just this one, in this case function is very nice. E to the power x remain constant and hence you get this one, but in general you will not get this one. For example, if you look at, instead of this one, if you look at fx equal to sine square x plus sine square x cos 2x, something like that, you might not get back f. All right.
Yes, sir.
So we want this as a product rule, right? So we know here it is product rule, right? So this is, we want to look at this function as gx times hx, right? Here also gx times hx, and we want the derivative, it is in terms of derivative of g and h, which is easy to calculate, which we did here, few examples, right? So, suppose fx equal to gx times hx, where g and h are differentiable.
So as far as I remember, if they are sufficiently differentiable, then fnx forms a series of differentiations of gx and hx where the coefficients are equal to
So have you done this in first year?
no, not really.
Okay. So you want this. So this is a theorem by Leibniz. So suppose if this is differentiable, I'll put on whole of R, but it's actually wherever it is differentiable, you can do it. Maybe let's write it the weakest, I mean strongest form, which is differentiable at x equal to a, then, well, we want actually how many times differentiable, not just differentiable. Infinitely times on R. So infinitely differentiable. Then we want f and x to be what? Gx h and x plus, what will be the next term?
nc1 g dash x h n minus 1 x.
Right, nc1 g prime x h n minus 1 x, right?
And the
Second
while
term would be
will follow.
nc2 g double prime x h n minus 2 x plus dot dot plus the last term would be gn x h x. All right.
Yes, sir.
Do you believe this?
You can check by induction.
Right. So proof is for n equal to 1. So for n equal to 1, it is the usual product rule. Product rule. So the important thing is only the induction step. So those who are not comfortable, I suggest proof by themselves. So this is very easy. Assume this is, let me call this 1. 1 holds for n equal to k. That means fk, that is fk x should be gx hkx plus nc1 kc1 kc1 g prime x h k minus 1 x plus dot 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 plus this would be, last term would be uh, g kx hx. Now take derivative derivative in the so-called in the previous expression, and use product rule. Rule in the right hand side, right? So the remaining proof is an exercise. So do compute this one. It's very easy. All right, but this is important because of the next thing. So next topic which we would like to discuss is Taylor series. Taylor's formula. Right. So have you heard of Taylor's formula before?
Yes, sir.
So was it there in the first year?
Yes, sir.
Okay. So what do you know about Taylor's formula? I don't want the formula. I don't want what is it actually.
Uh, we take a function and approximate it by a polynomial.
Right, approximated by a polynomial. Right.
We only worked out till doubly differentiable functions.
Worked out what kind of function?
Twice differentiable functions.
Okay, twice differentiable function. Right. Yeah, so what does it do to twice differentiable function? What kind of polynomial by which you can express?
Basically, a power series polynomial kind of a truncated power series polynomial where if there is a function f and we want to approximate it around a point a, then
Mm-hmm.
f of x can be approximated as f of a plus f prime a x minus a by 1 factorial and plus f double prime c where c is some some number lying between a and x.
Mm-hmm.
And f
Right.
double prime c x minus a whole square by 2 factorial.
Right. True. So suppose let me start with a simple function. So suppose Px is a polynomial. So a0 plus a1 x plus n x power n is a polynomial, right? Is a polynomial, right? Now, so the point is, so this is one form of the polynomial, right? And the same polynomial. So suppose fix a point. What should I fix? Alpha, let's say. Right, fix a point. Then you can always write px to be a naught plus a1 times x minus alpha plus alpha, right? A2 x minus alpha plus alpha square, right? And an x minus alpha plus alpha whole to the power n, right? So now you can expand binomial. So you can, expand these things binomially. So expanding the binomials. So maybe expanding just right. You get actually a naught. Maybe I should write alpha naught. Alpha is there, so let me write it b naught. B naught plus b1 times x minus alpha plus bn times x minus alpha n. Can you write that? Where b naught, b1, bn are constants. Right? Can you write that?
Yes.
Yeah, so how do you write? You just look at, let me do it for two, for polynomial of degree 2, that would be easy. And similar things you can do the later also. Plus alpha plus a2 times x minus alpha plus alpha squared. So that would be a naught plus a1 times x minus alpha plus a1 alpha plus a2 times x minus alpha square plus 2a2 alpha times, maybe I should write it down there, plus 2a2 alpha times x minus alpha plus a2 alpha square. So here you take a naught plus a1 alpha a1 alpha plus a2 alpha square plus a1 plus 2a2 alpha x minus alpha plus a2 x minus alpha square. So in this case, v naught is this one. So b naught is this one, b1 is this, and b2 is just a2, right? So you can expand other terms as well, and you get this expansion, right? So this is very important. This is very important. This is what is called Taylor polynomial at so x equal to alpha. And you see what v naught v1 is very clear. So bj so b naught is p of alpha, right? P of alpha. At x equal to alpha, you put all this becomes 0, you get b naught. b1 will be p prime alpha, right? So if you take the derivative, b naught b, this goes to 0, and here b1 remains, and all other terms when you put x equal to alpha, it will be 0. b2 will be p double prime alpha by 2. b3 will be p3 alpha by factorial 3, and so on. So bn will be pn alpha by factorial n. Factorial n. Now note, any polynomial, any polynomial right with yeah, so maybe I'll take this one as a function, but at this point, yeah, let us go beyond it. Suppose you, I mean, suppose uh, the point is, suppose p is not given now. Yeah, so I should note this one. So what, see, to look at this term, this one, what you need to know about just is b naught, b1, bn, right? So, so suppose, so note, suppose b naught, b1, bn is given, then the polynomial P is uniquely determined. Right? So if that means if summation bj x minus alpha to the power j from 0 to n is equal to summation b tilde j x minus alpha to the power j from 0 to n, then bj is equal to bj tilde for all j equal to 1 to n. Right? Is it clear?
Yes, sir.
So what's the statement? The polynomial is determined if that equality holds.
Polynomial p is this one.
Yeah.
This polynomial, whatever, yeah, this one is uniquely determined. So that means that what uniquely determined, that is, so yeah, what I mean by this is this following. That is, if this one, there is another one, right? This kind of stuff, polynomial, which both are equal at alpha. I mean, of this form, then this bj should be, so this is true for all x at least in an interval containing alpha. So you take just r for the time being. Okay, then bj has to be equal to bj tilde. Right? So you can take the derivative at alpha. Right? This is this two polynomials are so corresponding to b naught b1 bn. Yeah, maybe, yeah, right. So given b1 bn, you have a polynomial p, which is this one. And if you take this equal to bj tilde x minus alpha j, if happens there is some other bj's, then this has to be equal to bj. Bj tilde has to be equal to bj. That is the statement. So given these coefficients, which nothing but the derivatives, you can uniquely determine the polynomial. Right? So in other words, given the derivatives up to order n, we can uniquely determine a polynomial. A polynomial. Right? Okay. Just a minute. Anyway, I don't know where I kept it, but we have only 5 minutes. Right, so this polynomial p, so definition for a function If, let's say, A, B to are continuous such that f f prime dot f n minus 1 are all exist and continuous on AB, well, in, let me, oh, what I'm writing, I don't need this. This f prime all exists and continuous. Okay, that is fine. Then the polynomial px, which is summation, then for x naught belongs to open AB, the polynomial px, which is, this is x naught, okay, which is f j x naught by factorial j from 0 to n x minus x naught power n is called the Taylor polynomial of f of order n of order degree n. A Taylor polynomial of degree, sorry, this is not order, of degree n for f at the point x naught. All right. So we'll next time we'll describe first how this approximates, this polynomial approximates f, and then we'll continue further. Okay. Any question?
Sir, x minus x naught to the power j, right, and not n.
Ah, sure. Yeah. Thank you. So this will be j. True. Yeah. This will be j. Right. Yeah, so this is interesting because I mean, as you increase the degree, the more closer you will get to F, right? So you need differentiability of that order, then you can go more closely. Yeah. Any other question? Okay, all right, then we'll meet tomorrow again. So there will be a tutorial today, so they will explain some problems. Of course, there is no assignment, but they will explain some problems from a book. Okay, so see you tomorrow. Bye.
Sir, will there be tutorial today? Sir?